Hello there, my name is David Cater. In this video we're going to take a look at capacitors, some of the basic formulas and the values that we're going to want to be familiar with. So the capacitor is two parallel conductive plates and they are going to be insulated with a dielectric material in between. So when we hook it up to a source, we're going to start to charge one of the plates with electrons. Any electrons on the other side will be forced away because like charges repel, and we'll be left with an absence of charges and therefore a positive charge. So inside we'll be developing this very, very strong electric field. We'll be storing energy in the electric field, and that's kind of how we use a capacitor in DC or AC. We use it to store energy in a form, and that will be within the electric field. All right, so let's take a look at the physical properties of the capacitor and see how they will affect it. All right, so the capacitor itself is going to be measured in farads, and that is the unit. Okay, and so the symbol for capacitance is the big C, all right? So the capacitance of the capacitor is going to be sort of a rating of how much charge the capacitor can store and how hard or how much voltage we have to push to actually get those electrons to be stored, all right? So there's two formulas we're going to look at. The first one is the physical properties, right? And so the area of the plate is going to play a part in how easy it is to store electrons. The bigger the plate, the electrons aren't packed in as tightly, and so we don't have to force them in there as hard. So that's going to increase the capacitance. The material in between, the dielectric material, will have a constant given to it. Different materials have different constants, air, mica, anything like that. They're going to have a different value for this dielectric constant. It's actually going to change the way the electric field will behave inside, and it will start to distort the material in between and actually store additional charge that way. So the area, just to recap, and the dielectric material or dielectric constant are going to increase the capacitance of that system. Now what's going to have a negative effect is the distance between the plates. If we increase the distance, we have to put more and more voltage on to build the same strength of the electric field. So the distance is going to have a negative effect or an inverse effect. So we're going to put the distance below the formula, and therefore it's going to drop the value of capacitance as it rises. All right, so the big three, the area of the plates and the dielectric material in between with the distance between, that's going to be all of the physical properties that really dictate how much charge this thing can store when we apply an EMF. But we can look at capacitance a little bit different. Capacitance, which of course is measured in farads, could be defined as the amount of charge that we put on it, and this is going to be measured in coulombs. It would be, of course, a given number of electrons. So the amount of charge that we can store on it for the amount of force that we have to apply to it, or the voltage, which of course is going to be the electromotive force. All right, so our farad, if we have 1 coulomb of charge stored on our plates when we apply only 1 volt of EMF, that would be a capacitor that has 1 farad worth of charge, and that would be a very large capacitor. All right, so you can see them many times in the world, but most capacitors are typically rated in microfarads, so they're very, very small, but they can be quite large too, and 1 farad is fairly large. All right, so if we want to kind of figure out how much charge is on this plate, so another formula we can use, and this is kind of just a throwback to simpler times, and that would be if we want to figure out how many electrons are on it, we can say the charge is going to be equal to the amount of current going to the capacitor multiplied by the amount of time that amperage is flowing. And so if we simply break that down, the amperage is charge per second. The unit is charge per second, and time, of course, is in seconds. And so when we put those two together, we take Q divided by S multiplied by S. We can see that the S's are going to cancel, and all we're left with is Q, and there we go. So we can prove that I, the current, for a given amount of time, is going to dictate how much charge is on there. But we need to realize that in DC, the charge isn't going to be constant, and in AC, and so we have to take this sort of with a grain of salt with a little asterisk right beside it and learn about time constants. All right, so that'll be the last formula we look at. So the amount of time it's going to take for this plate to charge is going to be dictated by two things within a circuit. The first thing, for the time constant 1, is going to be how big the capacitor is. So the bigger the capacitor, the longer it's going to take. That makes sense. So the time constant will be bigger. And this will be measured in farads. And the restricting flow of the current, the resistance, is going to cause it to take longer as well. So it's a fairly straightforward formula. For the first time constant, you take the capacitance, multiply it by the resistance of the circuit. That gives you that value of time in seconds. You take this, multiply it by 5, and you have your all 5 time constants, and now you know how long it will take for any capacitor to charge from 0 volts up to maximum voltage, all right, which should equal the source, all right, in DC. Now, this is kind of just the intro to capacitors, some of the formulas we want to know, the physical properties, the electrical properties, how much charge is on there when a certain amperage is flowing, and of course, how long it's going to take for that to charge up in DC. All right, so I hope you enjoyed this video, and we'll see you in the next one.